So, hello, RubyKaigi. Before we start, a few words about us. A moment, sorry. My name is Zahary. The thing you should know about me is that I started my career as a game engine developer. Are there some game developers around here? Let me see some hands. Well, all right, we have one, which is not surprising because when you develop games, it's very hard to use a language like Ruby. You have to use something that can get you maximum performance out of the existing hardware. So this meant that I had to write in a language like C++, but deep down I really dreamt about being able to write in Ruby. TC?
So hello.
Jameson. Sorry. So this led me to get this idea of creating my own programming language that would be suitable for the task and has a simple goal to be as slick as Ruby and as fast as C++. And that's how I found the NIM programming language. I joined the development team 7 years ago, and I'm currently the second most active contributor after the main author, Andreas Rumpf. And this is my friend Alexander.
Hello. So I'm Alexander. Basically, I also work language design and programming languages. I started with some little. I started with doing some little toy projects in the beginning. Then I started contributing to some languages like Elixir and NIM, and currently I'm working on developer tools in NIM in most of my time. And in the beginning, I was actually a Python and Ruby web developer. I was also a part of the Ruby course in Sofia University, so that's where I fell in love with Ruby in the beginning. And mostly I used Ruby, like Ruby on Rails and web design, like I'm sure many of you. How many of you are Rails web developers? Yeah, much more, many more than game developers. And yeah, so I also used it for some toy GitHub projects, but nothing too much. So yeah, we're coming from Bulgaria. I'm not sure if any of you has been there. Has anybody been in Bulgaria from here? Oh, 3 people, awesome. So people in Bulgaria that come here usually show pictures of Sofia, but I live in Plovdiv currently. So yeah, it's like our version of Kyoto, I guess. It's 8,000 years old. It's very old, very cute, a lot of old buildings and cats and very nice pancakes. And also it's the cultural capital of Europe this year, together with one Italian city. So if you come to the Balkans or to Bulgaria, go and visit. People love it. So yeah, basically some things about Bulgaria. I'm sure everybody knows about yogurt, but we were one of the first Christian countries in Eastern Europe, but this didn't really happen easily. Basically, we started from Asia, and we were something like a nomad country, and we moved with houses everywhere, and finally we did end up on the Balkans, which was the first version of Bulgaria. It had some glorious moments, but we had some very powerful competitors, so we had to launch version 2 somewhere after the 1000th year. It worked very well for some time, but then we faced some evil corporations, and basically we had to close for like 500 years. And we had to fight for our freedom, and thankfully in our liberation war, a lot of nations came, and not the last one Japanese samurai fought in our liberation war, which was crazy. And thank you for this also. So after this, we got our almost final version of Bulgaria. one game company called the Red Army tried to apply a communism patch, but the ratings were very low and people hated it. So yeah, that's how we got here. And finally, we're back to Asia, where Bulgaria began in the first place, but only for RubyKaigi for now. So yeah, let's get back to the topic. Why are we doing this? I will explain.
So this topic is about talks about translating dynamic languages like Ruby to statically typed ones like C++ or NIM in our case. So why would you do that? Why would you leave the comfort of the great language like Ruby to try something else? And the most likely reason is that, for example, your project has grown big, you have many users, which, congratulations, this is a good problem to have, but this leads many companies to want to rewrite their systems in a different programming language. And this usually takes a lot of time, it's expensive, it's quite risky, and it would be nice if it can be done in a safer and more easier way. But there are few other possible reasons as well. For example, you may want to implement an algorithm such as, say, a cryptographic routine in just one single time in some kind of pseudocode, for example. And then you would like to translate this single implementation in many different languages so people from different communities can take advantage of this cryptographic routine. This could be another example. Finally, perhaps you would want to experience the useful capabilities and superpowers of Ruby during the rapid prototyping phase of your project, but you want to keep the option at all times to have an optimized, automatically translated version during all times. So you can ship the optimized version to your end customers while your developers are using the richness and more power of Ruby. So we've been doing projects that are roughly in this space for a few years already. It's all started with a project called Pseudo from my friend Alexander, which is more than 4 years ago. And he'll tell you a little bit more about it.
Yeah, so you can find it on GitHub, but it's not actively maintained anymore. But basically, the original idea came when I had a lot of projects which I wanted to do, which related to a similar goal. They had to do with somehow generating an algorithm or the same logic for something. A good example is, for example, parser generators. And basically the problem is that I had this logic figured out and it was very unsatisfactory because this seemed like the hard part, but in the end I was generating the algorithm in a single language. And it seemed that it should be easy to generate the algorithm once and to be able to automatically render it in as many possible languages as you can. And this applies to a lot of stuff like AP handlers or wrappers or even some kind of general purpose algorithm lib or something like this. So my solution was to use a subset of existing language. In this case, some kind of very simple languages like Python and Ruby that is very accessible and very nice for writing like pseudocode, and to target all kinds of other languages. So basically the two main differences to similar approaches were that I wanted to generate idiomatic code, so I used like an intermediate layer which defined like an universal language AST and universal language standard library, which was like a superset of all the other usual libraries like types, collection, functions, and all kinds of standard methods. And basically it's easy to declaratively teach pseudo how to recognize invocations to the standard library and how to map them to the target language in a readable way. So basically, this was nice and this was working well for small programs and examples, but I had to use very limited subset of pseudo because I was trying to do full type subset of Ruby or Python because I didn't even end up the Ruby version because it was very hard to do full type inference even on a small subset. So with time we find out we need a different approach, and that's Pythonim.
All right, Pythonim was created, the company where I work, it's called Status, and our goal is to create one of the first implementation of Ethereum 2.0. And you're probably not familiar, but the Ethereum 2.0 development is driven by the research team, which is working in Python. And so we at Status felt that we need a language that is kind of similar to Python in appearance, and that can express the same idioms in a similar way. And NIM kind of fits this bill, and it comes with the additional advantage that, as I mentioned, it's very fast, very efficient. The goal of Status is to ship Ethereum implementation for mobile devices and resource-restricted devices in general. So that's how we approach this project. We wanted to make it easy to translate the Python code that the Ethereum Foundation is creating, and we wanted to be able to translate the PyEVM, the existing Ethereum 1 virtual machine. And so in the first month of development of Nimbus, our Ethereum client, we made great amount of automated translation for roughly, I think it was nearly 50,000 lines of code. That what was not quite working, it needed some manual finishing touches, but in a very short amount of time, it was able to pass the test suite that was also automatically translated, and this gave us confidence that the project is implemented correctly. And over time, the code base has changed significantly. It has gone through several refactorings to make it more efficient and to take full advantage of NIM, but Pythonim has played its role quite well in the beginning. So there's some key differences between Pseudo and Pythonim. While Pseudo is looking at the program as a static snapshot, it just analyzes the source code at any given time. Pythonim is able to infer most of the information about the program through execution, through tracing. We'll talk a little bit about this later. And the other difference is that while Pseudo tries to be a system that covers all of these different programming languages, is basically the least common denominator of all of them, Pythonim is much more optimized to target specifically, was optimized to target specifically Python and NIM. And it was obviously developed with practical translation in mind, translating real-world projects. So today, we are announcing for the very first time the release of RubyToNIM. It's a tool similar to Pythonim, but intended for Ruby. And actually, both Pythonim and RubyToNIM are now built using a more general system that we call Linguist. We'll talk a little bit more about this later. So why did we choose Ruby as our second target? Well, first of all, because Ruby is awesome. That's no-brainer, right? But the second point is that Ruby is quite a challenge to translate because in Ruby, metaprogramming is so prominent, and there are many DSLs that most of you would believe that are impossible to express in other programming language, I think. And so we like this challenge, and that's why we picked Ruby as our second language. And so why NIM? I'll tell you a little bit more about NIM. As I mentioned, NIM is really fast. It's basically on par with C and C++ in most programs. But it has a garbage collector, so many of the APIs that you are used to in dynamic programming languages can be easily expressed in the NIM runtime system as well. But more importantly, NIM has really, really strong metaprogramming capabilities. So that's why we can imitate or recreate the expressive power of Ruby as well. I'll show you some examples of this. We start with something simple. I mean, Ruby blocks are so elegant. One of the major reasons why Ruby is so great. In NIM, they look almost just the same. You can introduce functions that take arbitrary blocks, do stuff with them, and so on. In Ruby, we have these small and beautiful DSLs, like, for example, Sinatra. In NIM, it's quite possible to create something that looks roughly the same. And there's one-to-one correspondence of program elements. And then in Ruby, you can build this more complicated DSL. For example, I've used Markby here, the old Markby as an example. And you should get the pattern by now. In NIM, it's very easy to recreate something that looks exactly the same. All of this is possible because NIM has very powerful support for compile time macros. If you know a little bit about macros, please, these macros should not be confused with the C and C++ type of macros, which are textual. They are much more like the Lisp macros. They take a piece of your program at compile time, they give it to a function that will be executed at compile time. It will transform this piece of program into something else, and the result of this transformation will become part of the final program. And in NIM, in particular, it goes a little bit further behind Lisp, beyond Lisp, I would say, because you have full awareness of the type system within these macros. And you can do overloading and play with the generic types and so on in many interesting ways. The limit's pretty much endless. So, I'll tell you a little bit more about how the general approach of Ruby to NIM, how does it work? Well, the key insight is that even though Ruby is a dynamic language, at runtime, the program the execution of the program manipulates concrete and specific values of specific types. Your function usually accept a specific class or an object like a list or a number or a string. And if we monitor very closely the execution of the program, we can assign concrete types to many, if not almost all of the functions. So what we do is we record a very precise trace of the execution using the tracepoint API, and we create a database. We're releasing also today a tool to do this. Basically, it's you can find it on this GitHub page. It can serve as a drop-in replacement of the Ruby interpreter, or you can also use it as a library to trace only certain files. When you execute it, it creates a database that includes the abstract syntax tree of all the loaded files in the program with attached type annotations. Like for all the functions, what were the specific types that were noticed during execution. So besides Ruby to NIM, these two could be used for several other purposes. We haven't explored them yet, but we feel it's worth investing time in them. One thing is, if you have a test suite in your program, you can run your tests with RubyDeduct, and it can build a database that can act as a language server for your text editor to provide much better code out to completion. Or perhaps you could execute your tests in a continuous integration environment and produce a web page, a browsable web page of your source code when you can click on the individual functions and type definitions and just navigate your program much more interactively. And finally, today there was a talk about the Ruby interface files that are useful in Ruby 3. You can use RubyDeduct to create this type of files automatically. One thing that I should mention, in order for this approach to work, it's very important that your code has good coverage. So it's important to have a good test suite. But as a Ruby developers, I hope you have existing and good test suites in your project. So as you can see, translating Ruby files to NIM is a super piece of cake. And this concludes this talk. And there is some time for questions.
Yeah. So indeed, the truth is that it's not so easy as it seems. So that's why there is most of this talk. There are some problems. For example, mock types. They're great for testing, but as you can imagine, they're just fake values that confuse RubyDeduct a lot because they don't really represent the original intention of the programmer as fields and types. Another problem is, for example, testing for invalid input, which passes strangely shaped data and stuff like this, which requires some more extensive exception analysis, but it's still not very easy to weed out. So there are more problems that we will talk about later, like some more dynamic portions of code, but a lot of those can be fixed by optional source annotations and project-specific hints or configuration, which should be very wide. Basically, I've almost never had to use it until now, but sometimes it's useful to be able to do this. The annotations are usually inline. They're just little commands, magic commands started with language, and for example, you can ignore something, or you can override return types or walkout types or something like this. And if it's needed, we can add some more hints to language. But again, this is only a last resort, and it's usually not needed for translating a lot of the code. But it can be still very useful if you want fully automated translation of bigger code bases. And in the future, we hope to incorporate basically Ruby 3 code annotations related to types, so this should come for free. So, yeah, basically another problem is overly dynamic code, the typing stuff like this. Very often, actually surprisingly often, a lot of functions are not so dynamic as we expected. So this doesn't happen so often as we thought, but there are several possible approaches. So basically, usually everything is good if you have basically similar values. Sometimes it's still easy to express some kind of variant or an overrided class or some other thing depending on target type system. But sometimes even this is hard. So that's why we can use heuristics and stuff like this. And sometimes we designed the RubyDeduct to be able to eventually gather statistics and see some anomalies and ignore them, or choose the most important type in some case, or to generate generic functions, which are more general in some cases. And sometimes the right thing is to just give up, because it's true that some portions are not, you can't really translate automatically stuff like dynamic method or instance eval, at least not yet. So if we can just tell the user you need to add some hints here, or you need to move this to a component that you port manually, and then we can auto-translate its invocations, that would be the best. And that's how we usually do it for real-world projects. So another important solution is why do we target so much, why do we insist the code to be idiomatic? If you've seen, for example, TypeScript output or any other transpilers, you see that the resulting code it's very dirty, and our hope is to be able to maintain the output. So it should work exactly as it would work if a human took style guide and tried really hard to write normal code. So usually other projects like Hex, the easiest thing is to just implement your own runtime, for example, Ruby runtime in NIM, and to just invoke it. But this is very unidiomatic, and it involves some overhead, and it's just not a beautiful solution. And after all, programming should be beautiful. So yeah, what happens in those cases that we talked about? Basically, you need to still export some parts manually, but our hope is to be able to automate most of the work.
So, a few words about how a typical project looks like. In a typical project, you have two repositories. One is the project you are trying to translate, and obviously the other repository, your translated code. In both of these repositories, you can have two branches. Basically, in the original source repository, you would have one branch where you put the annotations. And this branch should be relatively light. Only few patches should be in there, and it should be easy to rebase every time you want to sync with the upstream project. There may be conflicts from time to time, but our goal is to maintain the annotations light enough so rebasing is quite practical. And in the translated code, we also support some manual patches that will be applied after the automatic translation. And obviously here most projects strive to have 0 manual patches, but the system is built in a way that it can tolerate this kind of additional manual cosmetic changes, or how should I call them? One thing I should mention is that translating a project involves a lot of engineering insight. Typically, we would start by looking at the project and trying to create a map of its components. And very often, some of the components will be an ideal targets for replacing. And what I mean here is that they may be existing solutions in the target languages that you're planning to use. Or maybe it's just the component is written in a non-very efficient way, or in a way that is using Ruby in too much of a dynamic way, and so you really want to just replace this component without translating it. So our system has to be flexible in allowing you to pick individual components that you want to replace with manual implementations. So, my friend will talk more about this. Basically, it's usually not enough to just translate the code as it is. As he mentioned, we want to target idiomatic translations, and we achieve this through a term rewriting system that Alexander will tell you a little bit more about.
Yeah, so basically, the idiom part, that's the point that we have. Basically, we define a DSL that lets us easily define custom rules for recognizing and for recognizing as input portions of the input syntax tree and to generate target syntax tree. Here, it might seem that we are recognizing source, but this is just a declarative way to match on nodes. Everything this phase works with is our universal interlang tree, which is the same for all languages that we process.
And I should mention that what you see here is just a normal regular NIM code. It's a DSL written in NIM.
Yeah, indeed. So the ideal translation of idioms is that we don't, for example, in this case, if you translate Ruby to Python, you don't really translate this to some code to our runtime code map, but you find the common pattern in Python and you use this. And you can apply it to everything, like opening files or invoking methods from enumerable or everything, or using some web DSL or something like this. So basically, how does it work? It's inspired by several existing mechanisms, but it has some differences and it's adapted for our case. For example, we use some of the types that we found out to overload the patterns. Because, for example, if you iterate between different collections, sometimes you need to generate different kinds of code. And basically, it's very important to be able to easily declare the rewrite rules. So, yeah. Basically, we have this idea of standard library from pseudo. It sounds very official, and it should get some kind of specification, so it can be more obvious to outer people, because if this works well, it should be easy to add new languages and define their idioms and take a lot of the language functionality for free. And basically use a lot of our patterns for generating idioms in different languages. So how does it work? Basically, we have several stages. We have we applied those transformations, one for the input code, one for the target code, and we can apply some project-specific rules. And it's basically the most flexible part of our project, because in your project you can add your own models that add such rules, and they can tweak almost any part of the translation. So another important component is that when you're finished with all the analyzing and rewriting in language, we get the final TUI, and we define a way to generate code. So we're planning to port the pseudo DSL, which was very simple, and it made it quite easy to add support for new languages in a way. So it should take like 1 hour to add base generator support for new language. Of course, there are some gadgets, but at least most of it should be very decorative. So yeah, how does this work? We also apply some local type inference, because in the tools we catch the most high level stuff like argument types. And basically this is enough for our needs currently. So yeah, this approach shines in final projects. It's not the best for libraries, but when you use some framework that you have good rules for, or third-party libraries, it works pretty well, because you can, basically your end code works quite similarly, and it's easy to set boundaries between those libraries and your actual code. Basically, it's easy to translate only your business logic and to replace any other components, but whatever you need, either translations or some target language libraries or some kind of manually ported component. It's easy to be very flexible. So we needed an initial real-world project to test this hypothesis. And yeah, that's why we decided to focus on a popular Ruby project that fulfills these goals, and that's RubyKaigi. So we decided to create something like fast RubyKaigi, which should act like a drop-in replacement for RubyKaigi. It should eventually accept the same command-like arguments, and we're trying to generate very similar output. And our goal is to currently translate most cops. There are like 500 cops in it. So basically, for example, this is an example fully automated translation of one cop. On the left it's Ruby, and on the right there is Nim. You can take a look in the repository. There's some fully automated cops, and most of them have some implementation, some good translation that still needs some kind of fixes. So, for example, about the speed, yeah, basically the results so far are that we've translated fully only several cops, but we are adding new all the time. And the speed up is usually somewhere between 2 and 11 types. Usually with bigger code bases, the speed up is bigger and bigger. Some concrete results are those. The biggest project we tried it on was RubyKaigi itself. So basically, usually it takes, with the same settings, 16 seconds in RubyKaigi and second and something with our tool. So at least this goal seems to work for now. There should be a disclaimer that some of the infrastructure we had to route manually. We still have some wrong results because we needed to do some, I'll explain later about this, and we have to fix some things, but basically the speed remains like 2 to 10 times better with all those tests. We still run into some issues. So the three-seater problem is because RubyCop, it uses the parser gem. This is cool and nice, but parser is written in Ruby. So we decided that we can use like a C library in NIM. And three-seater is a good example of it. It's very fast, it's very cool. But still the resulting AST format is slightly different. So we had to do like a conversion layer that smoothed out the differences. But once this was done, it was still very easy to use because it was easy to add some rules and to imitate the API. So Languist translates the invocation, all the invocations of parser originally to the same invocations in NIM, and they just work. So that's one example of a third-party component that was easy to replace and still have automatic translations of its usage. Another problem was like, I don't know if anybody of you is familiar with RubyCop. They use node patterns a lot. It's basically a string DSL that it takes a string and it generates some pattern matching code for Ruby nodes. It's very nice, but that's very dynamic code. When you have like dynamic macros, method defined and stuff like this, that's very hard to translate. So still this is where the choice of NIM shined, because it was easy to map the DSL to a NIM compile time macros, because we could generate in a very similar way on compile time functions that do the same thing. And now it works almost in the same way as in Ruby, with the same invocation with string, but a lot quicker. So we got away this time, but another problem was that the cop files weren't really dry enough. Basically, we were generating correct code corresponding to the original one, but we wanted to use a NIM DSL that really removes any kind of repetition. So we added one more tweak, which is that you can have also like generator overrides. So when all the analysis is done and when you have the tree with the final tree, the final language tree, almost ready to be consumed, you can still rewrite it or you can still tweak it a bit. Basically, the lesson here is that we are trying to give as many escape hatches and tools and hooks in Languist, so you can tweak every part of the process and you can add whatever logic you might need. So, and in general, another good thing is that Languist can act as an automated refactoring tool, because basically we can just have the same input and output language. So for example, you can use the write system and all of our hooks to implement auto refactoring for Ruby or for any other languages, which is pretty cool. So a final problem is that symbols, we all love them, but they're still tricky to map to other languages, especially statical, because they're like a globally namespaced enum. So we're not sure, should we map them to string? Should we map them to some kind of enum? Should we map them to different kinds of enums? That's very hard, especially because you can use the same name for a symbol in different contexts for different purposes. So in the RubyCop project, most of the symbols that we needed were either the type of the Ruby node, or they were like method names passed to add offense, which signaled RubyCop what method to call, basically, again, a dynamic DSL. So what we did in the end was adding a special kind of symbol array when you can you can find where is a symbol used in a given context, and basically hard code your own knowledge about those enums, and then we can translate the information. This is not perfect, we know this, but it works well for our translation. It's very important because translating to strings, it leads to a lot slower code and stuff like this. So another solution was to maybe use type inference and connect it to some kind of smart dynamic info, but that's hard again. So basically the final thing that we wondered about this project was what stops us for translating all the cops. Basically there are some small technical problems, but nothing very fundamental. Yeah, like The location from the receiver is not very fixed. And mostly, we just need to add knowledge to deduct and to our rules about standard library and to Ruby itself. But again, that's just a matter of manwork and of manpower. And if we have enough time or enough demand, that's easy to do. It's not really the hard problem here. So a little bit for the future of the project. Zahary.
I'll have to be quick because we are running out of time, but what we see as the next possible step is to add more output languages besides NIM, because NIM is still pretty avant-garde and not used by many people. I think probably the Ruby community will enjoy adding support for Crystal, but the wider community may appreciate language like Java, C#, Go, and so on. And why not other dynamic languages as well? I mean, this could be a curiosity. And should mention that it's entirely possible to go the other way. It's actually easier. You can translate static languages to dynamic ones with a linguist. Some languages without a garbage collector are much more tricky, like C and Rust. Our ideas there is to perform some kind of automated lifetime analysis of the variables to see if the program you're trying to translate actually depends on the garbage collector or not. This is still obviously not resolved. It's experimental ideas and so on. One of the key questions we hope to get feedback from you is what are some other good projects that we should try to translate? We hoped to create an issue where you can vote in GitHub, but we ran out of time before this presentation. So maybe you can just come here and tell us. And I should mention that translating projects takes quite a lot of time still. It's not such an easy solution after all. But we believe that the crowdfunding model may be good for this. If the community selects a project and enough people contribute to create a fund, we can perhaps dedicate a single developer or teach somebody and support somebody in translating a particular project over a few months. So that's it. I don't know if you have any time for questions. No questions, sorry. You can find us here and if anyone is curious. Thank you very much.